An analog anti-log exponential computing circuit is shown here implemented with 3 op-amps and 2 matching bipolar junction transistor or BJTs that are implemented in the same substrate, on the same substrate in the same package and benefiting from the same junction properties. We want to show that this circuit effectively implements the anti-log calculation of Vn, which means the output voltage of the circuit is proportional to e to the power alpha times Vn, in which beta and alpha are constant or coefficients in the circuit as a function of circuit components that we can adjust. So we can control these guys. Alright, so how does this circuit work, and can we quickly prove this interesting relationship between the output voltage and input voltage in this circuit? To do so, let's focus on the op-amps 1, 2, 3. Let's make the assumption that the bias, so the supply voltages of the op-amp, let's say as an example, plus minus 10 volt are properly applied. You can see that the output of the op-amps is connected to the negative or inverting input terminal, indicating negative feedback is properly applied for all the 3 op-amps. So we can say op-amps are properly biased. I'm going to write it here. So op-amps are properly biased with the supply voltages applied, and then negative feedback is dominant and available for each op-amp. Therefore, virtual short is valid for each op-amp, which means the voltage at positive input terminal should be equal to voltage at negative input terminal, enforced by negative feedback. We can see that for all the op-amps, the positive terminal or non-inverting terminal is grounded. So that means because of virtual short, the negative terminal should be at virtual ground or 0 that I'm going to write. Okay, so let's focus on op-amp 1. We have Vin applied at the left side of this potentiometer of max 50K. So on one side we have 0, on the other side we have Vn, which means there is a voltage drop across potentiometer which is equal to Vn. I can find the current that is flowing through this potentiometer. I1 is Vn, the voltage across the potentiometer, divided by the value of potentiometer in kiloohm. Now this current can only continue through the 1 kiloohm nominal Tempco, which is the temperature compensating resistor or precise or precision resistor. So temperature compensating resistor. These are, let's say, very precise resistors with 1 kilo ohm. So I'm going to write it here. R resistor of Tempco is equal to 1 kilo ohm at room temperature. By room temperature I mean roughly 27 degrees C, which is equal to 300 absolute degree, which is 300 Kelvin. So at 300 Kelvin we can make the assumption that there is a 1 kilo ohm value of this temperature compensating resistor. I'm going to talk about it later, but for the time being, and for that resistor, just bear in mind that I'm going to talk about PT146, which is one good example of such temperature compensating resistor. So PT146, that's the name of this resistor. So now component number. So we have plus minus voltage drop across this resistor because this current is passing through it, and we can compute that voltage drop, which is V, let's say RT, or let's say just VR, and that allows us to compute the voltage at the output of the op-amp, which happens to be at the base of transistor 1. So this is basically VB1 for transistor 1. We are at the base of that transistor. Okay, how do we do that? We can write VB1. So let me change the color. So we can write VB1 is equal to 0, that is on the left side of the Tempco resistor, minus the voltage drop across that Tempco resistor. So is equal to 0 minus RT, the value of the resistor, times I1. This current. So we can substitute for I1, so minus RT times Vn divided by the value of potentiometer. Okay, so we're going to keep this. Basically, I just showed that we have minus RT over P times Vn. That's the value of voltage of base at base 1. Now, the plus minus VBE, the base emitter p-n junction of transistor 1, is a function of the current that is flowing through the collector of transistor 1. That becomes roughly the current of emitter. Now this current is coming from through the 10K resistor, because whatever current coming this way has to continue this way. Again, it cannot flow through the input terminal of the ideal op amp, because input terminal of ideal op amp has practically infinite impedance. So how do we calculate this IC1? Well, on one side we have 10 volt, on the other side we have 0. So I can easily compute this IC1 by just saying IC1 is just 10 volt, the voltage drop across 10K basically, divide by 10K. That is what I have here, which means 1 milliamp. Okay, so how are we gonna apply that? I can say here, I know VBE1 is the voltage of base emitter or a p-n junction of transistor T1, so I can apply the Shockley junction equation, which says voltage of a p-n junction is just ideality factor eta times Vt, the thermal voltage, which I'm going to just quickly show, and then natural logarithm of, let's say, IC1 divide by the saturation current Is. Since both transistors here are mirror, basically they are matching transistors on the same substrate and in the same package, we make the assumption that saturation current is the same for these transistors. So that's why I'm just writing Is. So in this Shockley, so this is the famous Shockley p-n junction IV current voltage equation, and in this famous equation we are saying that eta ideality factor is roughly 1 for the silicon based p-n junction transistors, and Vt thermal voltage is K times T over Q, in which K is Boltzmann constant, 1.38 times 10 to the power minus 23. Q is electron charge, which is 1.6 times 10 to the power minus 19. Temperature is the junction temperature in Kelvin, absolute temperature. So we can say KQ T0, which is 300 Kelvin, times actual temperature of junction divided by T0. So these can cancel out and we get back to the actual equation. We know this value, if you compute just multiplying these values times 300, you get to 26 millivolt. So this is roughly 26 millivolt times actual temperature over 300, which is the T0. So let's keep this. Vt is just this. I'm gonna substitute. So this is equation, let's say 1. I am going to use equation 1, and knowing that ideality factor is practically 1, so I'm not going to write it, but instead of Vt, I'm going to substitute from equation 1. So I'm going to write 26 milli volt, and then I have T over 300, and then natural logarithm, and then we have IC1, which we just computed 1 milliamp. So 1, I'm going to write it here, 1 milliamp divide by Is. So what is the problem here? The problem here is, this is good that we found this equation, and I'm going to refer to it as equation, let's say this is 2 and this is equation 3. So this is equation 2 and the other one is equation 3. So it is good we found this, but here is the problem. First, we have, for this voltage of base emitter of transistor 1, we have a linear dependency on temperature, which is here. So as T is increasing or decreasing, and again T is the temperature of the junction of transistor, then the VB is changing linearly. Worse than that, Is, or the saturation current of these transistors, is heavily exponentially depending on temperature, as if when temperature is changing by just plus minus, let's say 25 to 30 degrees C, just that much, which happens a lot actually in real life, then IS actually changes by 10 times or even more. So this can easily change by 1 or 2 orders of magnitude with just a few tens of degree of temperature change. So we really want to get rid of IS in this equation, and hopefully also somehow get rid of the linear temperature dependency. And that's the beauty of this circuit. So let's take a look at what is happening. Okay, so I'm gonna now write the equation for the VBE of transistor 2 with the same idea. So I'm gonna just put this aside. So let's park this for now. And with that aside, I can continue. So with that aside, I can continue and write this. So I can say again, applying the Shockley p-n junction IV equation, current voltage equation for p-n junction, I can say VBE2 for transistor 2 is equal to eta VT. Eta is 1, so I'm gonna just say VT, and for VT I'm gonna again substitute using what we found here. So 26 times T over 100, so 26 millivolt, T over 300, and that's my VT, and then natural logarithm, and then we have IC2 log of IC2 divided by saturation current IS. So what is this IC2? That is effectively IE2. This IC2 again cannot come from the negative terminal because the input impedance of op-amp is infinite. So this IC2 can only flow through the RF resistor and continue through the transistor. So on one side we have 0, on the other side we have Vout. So the voltage drop across this resistor RF is plus minus Vout. So we can compute IC2 easily by just saying IC2 is equal to Vout divided by RF. So here I'm going to substitute. So I'm going to say therefore is equal to 26 millivolt T over 300 times log of IC2 is Vout over RF divided by IS. So it's nice we found this equation number 4, but again it suffers from the same problems that we found before. We have a linear dependency on temperature. We have a worse than that dependency on IS, which is heavily exponentially dependent on temperature. So what else going on in the circuit? Well, look at the common emitter here. So there is a voltage of E, which is voltage of emitter of both transistors. I can say V of E1 equal to V of E2. Obviously we have the same common emitter, so I can substitute for these guys. For V of E1 I can say it is just voltage of base 1 here minus the voltage drop VBE1 to get to VE1. So it is VB1 minus VBE1 equal to, so this is saying V of E1 equal to V of E2. So V of E2 I can say is 0 because the base is grounded, and then minus VBE2. So minus VBE2 to get to voltage of emitter. So I have 0 minus VBE2. Great. I'm gonna just substitute from for VB1, VBE1 and VBE2 using equations 2, 3 and 4. So I'm gonna do that exactly. Substituting using equation 2, 3 and 4. For VBE1 I can say it is equal to this that is written. So minus RT times Vn minus RT over P times Vn here. And for negative VBE1, I'm substituting for VBE1 from equation 3. So 26 millivolt T over 300 log of 1 milliamp divided by IS. Divide by IS equal to, for minus VBE2, I'm going to substitute from using equation 4 that says VBE2 is equal to this guy. So I'm going to just write minus 26 millivolt T over 300 log of Vout divided by RF divided by IS. Now you can see the benefit of this whole exercise and this whole way of circuit designing, because if I move this guy to, because if I multiply both sides by a negative so that I get rid of this negative sign, so this becomes positive, 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 and then reshuffle things around, I end up with this outcome: 26 millivolt T divided by 300 log of Vout over RF divided by IS divided by 1 milliamp divided by IS equal to RT times P, RT over P times Vn. Now, the real nice thing happened. IS disappeared. So we get rid of the major temperature dependency via this technique that is, or implementation that is shown here. So as the next step, all I need to say is, therefore, I can say now the equation becomes as simple as 26 millivolt, or I can move. I can also move this to the other side, so it becomes simply ln, and so it's ln Vout divided by 1 milliamp times RF equal to, and we have 300 divided by, so I'm moving this to the other side, so 300 divided by T, and then 1 over 26 mil, so 1 over 26 mil means 0.026, so this is the result of moving these guys to the other side. And we have RT over potentiometer P times Vn. Okay, so one thing I can do is I can set the value of RF to 1 kilo ohm. That is what I can do. So I can set the value of RF to 1 kilo ohm. So this guy to 1 kilo ohm. If I do that, then 1 kilo ohm times 1 milliamp becomes 1 volt, and therefore with RF set to 1 kilo ohm, I get, so let me go back to the same color that I had, consistency. So I get log of Vout, because the denominator becomes 1 volt, so it becomes log of Vout volt over volt, so that's it, equal to, the other side here is interesting. RT is now the resistance value of the temperature compensating resistor, or Tempco. Note that it's important that this 1 kilo ohm Tempco is connected thermally to the junction of the matching transistors. So this should be thermally in contact with the junction of the matching transistors, so that this 1 kilo ohm Tempco exactly experience what the junction of these transistors thermally experiencing. So that is the practical note. If we do so, one interesting thing happen is Look at the PT146, this precision resistor or Tempco resistor. It has a positive temperature coefficient 3500 ppm. So what is the meaning of that? The meaning of that is this. It means RT, or the value of the resistor, the value of resistor as a function of temperature, is changing like this: 1 kilo ohm if you're at room temperature. So if you're changing from room temperature, so this is room temperature, 300 Kelvin, and if you're changing, deviating from that, then per degree C, you're gonna face 3500 divided by, so it's part per million, so that means divide by 10 to the 6 or a million, and that's it. So that is meaning that the value of resistor as a function of temperature is like this, linearly changing roughly, and it's very little change, but it is a change. So the nice thing is this division is roughly 286, and for that purpose we can make the assumption that it is so let me put it this way, is roughly 1 over 286, and 300k over 300 over 286 is roughly -1. That cancel out with 1. So this is roughly equal to 1 kilo ohm times T divided by 286, roughly. So this is a positive temperature coefficient, so that's why we say it's PTC, positive temperature coefficient, and then we say Tempco, temperature compensating resistor, this PT146. As temperature is increasing, the value of resistor is increasing. We have negative temperature NTC basically, but it's not here. This is PTC. So let's go back to here. I'm going to substitute for RT using equation number 5. So what I can write is now this. I can write is equal to 300 over T, 1 over 0.026, and for RT I am just writing this guy, which is 1K over P, which is the resistor of potentiometer in kilo ohm, and 1K is coming from this 1K, so 1 kilo ohm, and we have T over 286 Vn. Very nice. So this shows the importance of the benefit of having Tempco. So all I'm trying to say is the combination of matching transistors here helps us to get rid of the IS. That's the benefit of matching BJTs, and the existence of Tempco or temperature compensating resistor in this example allowed us to finally get rid of the linear temperature dependency. So we nicely get our exponential calculator or anti-log calculator with minimum temperature dependency, which is one of the hard parts. So is ln Vout is equal to 300, and then we have I would say over 286, so this guy, and times 1K over 0.026 times P times Vn. I can set the value of potentiometer P such that this thing becomes, for example, 1. So it is my choice. If we do so, P is roughly 40K. So if we do that, then the equation becomes log of Vout is equal to Vn, which translates to, or become effectively, it becomes Vn, Vout is equal to e to the power Vn. So we proved it. we proved that in this interesting circuit, the output voltage is just antilog of input voltage, or basically V out is e to the power V in. In this case, I designed the circuit specifically in such a way that beta is 1 and alpha is 1 as well. So you can see we have 1 and 1. So if we wanted other numbers, we could also do that, but we needed different choices of components. So to achieve exactly this with minimum temperature dependency, I needed to set the potentiometer P to 40K and RF to 1 kilo ohm. So I hope that this example is helpful to show how we can practically realize anti-log computing analog circuit, and what important temperature dependencies we need to consider in the circuit. I hope this is helpful. Thanks for watching.